Welcome to Calculus. Today we will investigate how to find area between curves that are defined as functions of x. We'll take a look at two examples where we find this type of area. Our first example involves two functions, y equals 2 times the square root of x and y equals the square root of x. And we're interested in the interval from x equals 0 to x equals 4. So to help us visualize the area that we're trying to calculate, I want to start off by graphing these two functions. So just to kind of anticipate graphing, I'm going to create a column. In fact, 3-column table here so that I can see both of my functions here in the table, and then it helped me as I go to graphs. So I'm just going to put x here, and I'm going to include all the way to 8. I know our interval is just to 4 here, but to get the graphs, let's carry that out to 8, since that's the extreme right-hand side of our x-axis. And what I want to do then is I want to generate values for these two functions. So we'll put 2 square root of x and also just square root of x. And we could do some of these values just by plugging in numbers. If I were to choose the domain values that were perfect squares, 0 would work. So if I plugged in 0 for x here, the square root of 0 is 0 times 2 is 0. And we see the same thing for square root of x. The next value that I could just calculate pretty easily would involve 4. So if I plugged in 4 into 2 square root of x, that'd be 2 times the square root of 4, which is 2 times 2, or 4. And then the square root of x, square root of 4 is just 2. So we can kind of see, at least initially, how that's comparing between the two functions for the same x value. Now for these other values, I really need to enlist the aid of a calculator. So I'm going to head over to the calculator just to generate table values for the non-perfect squares. So I'm just going to click the graph feature, and I just want to input the two functions. So 2 times the square root of x. And that gives us a nice view of that graph. So it's a square root function that has been stretched vertically. Let's input our second function, which is just the square root of x. And that's given us a good view there. So we can kind of visualize, we're trying to find the area between the blue and the red curve. I'm going to grab a table though, so that I can recreate that on my screen. So I'm looking at the split view here. The values we had calculated already look great. We got 0, 2. Well, in fact, we didn't include 1. We could have. But then these others are very much irrational decimal expansion. So for 2, the value is 2.8284. For 3, it's 3.464. 4 is 4. We had found that one. 5 is 4.472. 6 is 4.899. 7 is 5.292. And then the last value we're going to pick up is 8, 5.657. When I scroll over to just square root of x, I see the same decimal type values. They're just half the value of my other function, since that one has the multiplier 2. So I'm going to record these as well. These have a maximum right under 3. So I'll record these all the way back to 0. And what I want to do then is take that back to the note screen really quickly. And what we'll do there is we'll fill in our table, and let's graph those functions. So I did kind of overlook this one, that's 2, but then let me fill in these decimals. So 2.828. For 3, it's 3.464. Skip over 4 here, we had that one already. 5 is 4.472. 6 is 4.899. 7 is 5.292. And 8 is 5.657. we'll go ahead and graph that function. So I'm going to graph here starting at 0, 0, 1, 2, 2, 2.8, 3, 3.4, 5. I'm sorry, 4 is exactly 4. 5 is 4.472. 6 is 4.899. 7, 5.292. And 8 is 5.6. So definitely we see that stretched square root curve. And then let's finalize our table for the lower function, the square root of x. So 0, 1, and then square root of 2 is 1.414. That's pretty recognizable. Square root of 3, 1.732. Square root of 4 is 2. Square root of 5 is 2.236. Square root 6 is 2.449. Square root 7, 2.646. And lastly, for our table, square root of 8 is 2.828. And we'll graph that second function. So we're looking for it to be below this other one, 1.414, 1.72. So I see this blue curve is going to be entirely below the red one. And we are looking for that feature when we're calculating area between two curves. One of them needs to be below the other. 6, 2.4, 7, 2.6, 8, 2.8. So there's my two functions. All that's left for us to do just now is to locate my interval. So it's from x equals 0 to x equals 4. So I'm just going to highlight or shade, in fact, in between my two curves. And really, this is visually what I'm trying to calculate the area of. It's this slice of area in between the two graphs. So that purple region, ultimately, I'm trying to describe what is the area of that purple region. Okay, so we've got it all filled in there, and that helps us to visualize that's really what I'm calculating. So once I've graphed it and visualized it, I want to set up an integral for area. So just in general, the way that we would calculate such an area is that it's going to equal the integration from a to b. So for us, that's going to be 0 to 4. In fact, let's start setting it up. Ours is going to be integral from 0 to 4 of the upper function, we'll just call it f of x, minus the lower function, g of x. And what we need to note here is that really f of x needs to be greater than or equal to g of x. We'll see in a moment what we've got to do if that switches partway through for our two functions. And then we're going to multiply by the ever kind of decreasing width down to almost 0 dx. So let's fill in with our specific function. So we're going to calculate area from 0 to 4. And my f of x, which is greater than my g of x, is going to be 2 square root of x. And my g of x is going to be square root of x dx. So there's our setup. And at that point, I just want to simplify and integrate. So I see that my functions really are the same function. They just have a difference in coefficients. So 2 square root of x minus 1 square root of x is going to just be square root of x dx, which to help with the integration, I can call that x to the power of 1/2. And at that point, I'm ready to integrate. So I'm going to add 1 to that power of half. That'll be 3/2. And I'll have a coefficient that is the reciprocal of that. So I'm going to have a coefficient of 2/3 x to the power of 3 over 2. And I'm going to evaluate that from 0 to 4. So we're ready to apply fundamental theorem of calculus here by plugging in my limits of integration. So 2/3 times 4 to the power of 3 over 2 minus 2/3 times 0 to the power of 3 over 2. So I see there in my expression, this one in red is going to cancel out to 0. So all of my area is represented in this first multiplication. So I'm going to evaluate here 4 to the power of 3/2. Remember that denominators are roots. So square root of 4 is 2, and then I'm going to raise that to the power of 3. So 2 to the third power is 8. And then 8 times 2/3 is going to be 16/3. And that is complete. That represents the area of that purple region in between my two graphs. So for this example, we just had one point of intersection between my two functions. Let's take a look at another example where I see something a little different. So here I've got y equals x cubed plus x squared minus 5x. So a nice cubic function. So I'm expecting that one arm of this function is going to be headed towards negative infinity, one arm towards positive infinity. My second function is the identity line, y equals x. So I want to again start by graphing my two functions. And so just to anticipate that, I'm going to create a table like we did in our first example with 3 columns. And I'll use the same kind of setup here, but I want to adjust my domain. And I've kind of got some insight into how the graphs work. Notice I don't have an interval from some x value to another x value. I'm really looking for where do these two curves intersect. In fact, let me write that, because that is going to be how I determine my interval for my limits of integration. Where do the curves intersect? So I don't really know, just looking at these two functions, where they do that. So I'm going to include kind of a more central slice of my domain. So I'll go from -3, -2, -1, 0, 1, 2. We could go 3. And I'm going to input these two functions like we had done. So the upper one, well, we don't know yet. So I'm going to just put the first one, x cubed plus x squared minus 5x. And then our second function here, x. That second one we can fill in immediately. The identity function, whatever x is, y is the same. So -3, -2, -1, 0, 1, 2, 3. In fact, I can graph that function. It goes from corner to corner. And that's pretty convenient. So definitely y equals x is a good function to have. It's easy to graph. So for us, what we need to catch is a table for this middle function, the cubic function. So again, what I'll do is I'll enlist the aid of a calculator to generate that, and it'll help me visualize these two graphs. So we'll create a new graph screen, and we'll input our first function there, the cubic one. So x cubed plus x squared minus 5x. Go ahead and click enter there. So that's got that very classic cubic function shape. Definitely the left arm is headed towards negative infinity. The right arm's headed towards positive infinity. And I just want a table here. So I'm going to go to menu, create the table. And we had wanted to choose values from -3 and onwards. So -3 is -3, but then it really grows quickly. So 6, it's reaching a maximum somewhere between -2 and -1, or in that neighborhood. And then it starts to decrease again back to the origin. Rapidly decreases down to a minimum somewhere around +1, and then begins to climb really quickly. So our last value is going to be 21 here for our table. So I'm going to record those values, take it back to the notes screen, and I'm going to populate our table. So it starts off -3, -3. And one thing I'm noticing is that those values, specifically these two y values, are the same. So where the curves intersect is at -3. So I see that's one of those values. Just continue on here. I got 6, 5, 0. And again, I'm seeing another point of intersection. Just as a note, I wouldn't always see the x the same. What I'm really checking is where are my two function values the same. Just a coincidence that my x's were also that value. So then at 1, it's -3. 2 is 2. And again, I'm seeing all this the same. And then 21. So I see those 3 points of intersection. That's going to help me determine my intervals of integration here. So I'm going to start, let's graph -3, -3. -2 is 6, so that's where it really grows and rises up above the x-axis. -1's at 5, and then 0, 0. So on the left side here, if I were just to sketch this in, this cubic function rises very steeply back to 0. And then let's keep graphing. So at 1, it's -3. So what I see it past 0 is that the cubic function falls below the identity line. And then at 2, it's back at 2. And then 3 is off my graph at the value of 21. So in terms of our graphing here, we're really looking at that type of function. So what I want to do again is just highlight here what I'm actually trying to calculate when I'm saying what's the area between these two curves. So definitely this region on the left where the cubic function is greater than the identity function, that's part of my area. And I also have a second region here, which is this lower part to the right of 0 where my cubic function falls below my identity function. So there's really two regions here that I'm trying to calculate. Now, to respond to the fact that when I set up my integral, my f of x needs to be greater than my g of x, I have to write two separate intervals. So let's set it up here. So my first integral is going to be that purple region. So I'll write here area equals the integration. So I'm just picking up from my table. My x value is -3 to 0. And I'm going to put my function that has the greater y value first. So the one that's going to do that for us is this cubic function. So it's going to be x cubed plus x squared minus 5x minus the lower function x dx. And that's the region we've shaded there in the purple. Now I got to pick up with the green region from 0 to 2. And those are the points of intersection there. So 0 to 2. But now my order is different. My identity function has a higher y value than my cubic function. So it's going to be x minus x cubed plus x squared minus 5x. So when I got two functions that intersect more than once, and I'm trying to find the area between them, I've got to set up multiple integrals to represent the different regions. Once I've got it set up, we're ready to integrate. So let's deal with that first one in purple. So I can do a little combining of like terms. I'll write integration from -3 to 0. And I see that I got -5x minus x. So that's going to give me unchanged x cubed plus x squared, but now minus 6x dx. And then picking up with the green function, I can do something similar. Integration from 0 to 2 of really what's going to happen here is everything will become negative. Negative x cubed minus x squared. And then x minus negative 5x, that's going to change 5x to positive, so plus 6x dx. And we're ready to actually integrate at this point. So now I'm going to write that this is equal to 1/4 x to the power of 4. We're working on the purple integration first, plus 1/3 x cubed plus negative 6 times 1/2 x squared. And we're integrating that from -3 to 0. And then we'll pick up with our second expression. So I'll just write it slightly below here, plus, so it's a -1 there, 1/4 x to the 4th, plus, again, I got a -1 times 1/3 x cubed, and then plus 6 times half times x, and that's integrated from 0 to 2. Once I've got that integrated, now I want to simplify, reduce, and start plugging in values to integrate according to the fundamental theorem of calculus. So my first version is going to be 1/4 times, so I'm starting from -3 times negative, in fact, I'm sorry, let me get that order correct. Fundamental theorem of calculus says start with the upper limit. Okay. So I'm going to put in 0, but one thing I'm seeing is that all these terms, so minus 1/3, plus 1/3, I'm sorry, I'm getting confused by the coloration, 0 cubed, and the -6 times half is -3 times 0 squared. So nothing's going to come out of that. That's all 0. Minus 1/4 times -3 to the power of 4 plus 1/3 times -3 cubed, and then -3 times -3 squared. So that's where we're going to get sum of values here. All right, we'll set up for our second integral. So plus, and again, -1/4. I'll just wrap the -1 in the quarter as one coefficient, times 2 to the power of 4 plus -1/3 times 2 to the power of 3 plus 3 times 2, that should be squared there. So I'll get something again out of that expression, minus and again, this is for the second expression, but what I'm going to see here is that this is all going to zero out as well. So it's going to be -1/4 times 0 to the power of 4 plus -1/3 times 0 cubed plus 3 times 0 squared. So nothing's going to come out of that because that's all zeros. So basically it's my middle two expressions. So what I want to do is I'm going to simplify, I'm going to reduce the powers, and I'm also going to multiply times the fractions, and I'm keeping an eye. I got a lot of fractions with denominators 4, 3, or no denominator. So I'm going to write them in terms of a denominator of 12 so that they're all the same. So to kind of get there, let me do this step first. So my next step is going to be that this is, put a negative out front. So I'm working on this group in light blue. So that's going to be -81/4 when I raise -3 to the 4th power. I kind of combined my numbers there. 81 over 4 plus negative 27 over 3. And then plus negative 27. So that just reduces it down to just numbers. And then plus picking up there, negative 4. That's negative quarter times 2 to the power of 4 plus negative 8/3. And then plus 12. Now I'm ready to get the denominator of 12. So it's negative 243 over 12. And I'm bringing it all out of the parentheses now, plus 108 over 12, plus 324 over 12. And then picking up with the second group, minus 48 over 12. That's negative 4 scaled to be over the denominator of 12, minus 32 over 12. And then plus 144 over 12. And adding all up, we're going to get this value 253 over 12. And that is the area defined by these two curves, x cubed plus x squared minus 5x, and the identity function x. Thank you for joining for this investigation of finding the area of a region enclosed by curves that are defined by x. See you soon.